Okay, let's get this show on the road. Hello, everyone. Hope you're well. Last class, the feels, let's get it. Let's get this spread. Let's finish up. And I'm actually meeting you guys next week. So technically it's not the last class because you guys taught me into an extra class. I didn't want to do it, but Kale threatened me and I'm not going to mess with that gangster. So I decided to acquiesce. Okay, let's actually just jump in though. Let's finish up, get this, stay focused, get what we need to get to out of the way, then we can monkey around later. And let's just, let's continue. So last time, very excited, Jason was very excited. Hopefully some of his energy ran off on you guys. I haven't seen him type in all caps since this lecture. So I don't know if he's starting to wane, but we're going to continue. We are, well, yes, I assume we're having class on Monday. So yeah, all right. Okay, so last time we started talking about partial derivatives. Pretty much partial derivative is just you're taking the derivative with respect to one variable at a time. So mechanically, forget about conceptually what's going on. You don't actually need to know too much conceptually about what's going on. However, computationally what's going on is you pretty much pretend every variable is constant except the one that you're interested in taking the derivative with respect to. Everyone else pretend they're a number. They might as well be some number and you're taking the derivative. Basically what this is, it's like you're slicing through something with a plane and you're getting a curve and you're finding the tangent line that goes in the direction of one of the variables at a time. And we'll talk about some of the consequences of that, or I guess maybe lack of consequences of that later on. But we did that. So first of all, I told you guys there were different notations. There was the Leibniz notation that we have, and there's the subscript notation. We're actually going to talk about that a little bit more today as well. There is no prime notation because it's just too vague. When you have a prime, you don't know who the prime belongs to because you can take a derivative with respect to several variables. So when you have multivariable function and you want to take a derivative, you have to say who you're taking the derivative with respect to. There's a way to take a total derivative, but it's way above our pay grade. That's a whole other class, and you need a lot of linear algebra. This is the definition, the limit definition of the partial derivative. Pretty much you'll notice that for the partial with respect to x, only the x part gets changed by the h, and for the partial with respect to y, only the y part gets changed by the y. Conceptually, this is what's going on, as I mentioned here, and we can move on. So we went through computationally and started doing some stuff, and we learned that, well, when you take the partial derivative with respect to x, it's just pretend all the y's are constant. When you take the partial derivative with respect to y, pretend all the x's are constant, and just you follow all the derivative rules as you normally would. So product rule is still a thing, quotient rule is still a thing, chain rule is still a thing, all that good stuff. There's still things. Everything you've learned about derivative is still true. Here you're just kind of pretending every variable except one guy is a constant while you're performing all of those rules. Otherwise, everything is pretty much the same. We also learned, though, someone else is coming in here, that we can do implicit differentiation. And in fact, we can actually do a shortcut for implicit differentiation. We can get this nice little formula here. Whenever you want to actually find the partial of something with respect to something else, you can bring everything to one side, call that big F, and you take the partial derivative ratio in reverse order. So if I want the partial of z with respect to x, all I have to do is big F sub x divided by big F sub z, and then take the negative of that. And this is actually doing implicit differentiation. So this is a small part. This is about, there's a theorem that tells us this, and it's about half of what the chain rule is in higher dimensions. You'll learn another variable of the chain. You'll not learn a more expanded version of the chain rule in the next class. However, when you get to the next class and your 212 professor is telling you about this and he seems all excited, hey kids, you want to learn a faster way to do implicit differentiation? Don't let him know that I already told you. Pretend to be excited. You don't want it to fall flat, okay? So he's going to tell you Hey kids, this is going to be really exciting. And you're going to be like, yeah, I already saw this. Just pretend and act excited anyway. Just be like, wow, professor, that's amazing. Just put on your best acting skills. Jason, I'm looking at you. All right. Now, we did that and we kind of ended there. So what we're going to do now is we're going to jump right into another example, which now there are 3 variables. So this is a function of 3 variables. So its graph lives in 4 dimensions, but I'm still going to ask you guys to take some partial derivatives. So here's a function I would like you to find. Let me make it a little bigger so that you can see. I would like you to find the partial derivative with respect to x, with respect to y, and with respect to z. And it's more of the same, nothing really new to see here. It's just almost kind of a refresher for what we did up to yesterday. So let's see who can remember. All right, do I have any volunteers?
Oh, I can do this.
All right, Jason's
Well,
gonna do.
e
Jason,
to the z.
wait, hold on, wait. Let me just settle the volunteers first. So Jason's gonna do the first one. Who wants to do the second? Partial with respect to y.
Kayla, want to try?
Whoa, Jason's like calling her out. or is it
out?
So now Natalie, all right.
Yeah, Natalie, you go.
Anyone want to save Kayla?
How about I try the FC?
No. No, so Natalie, you're definitely going. We're trying to save you from your fear of public speaking here. Abdul Rahman. Okay, go. Jason.
Okay, you're getting me warmed up on this. Are you ready for this? Well, okay, here's the answer for f base to the x. As you can see, x e to the z power plus ln parentheses x y z. What you have to do is just take the derivative in respect to x and ignore the y and z and treat them as constants. So what you would do is just take the derivative of the x, think about the product rule, but ignore the z and the y. Just take the derivative of the x. So if we take the derivative of in respect to x, it would be ez, but plus e to the z power, plus, do you see this ln parentheses xyz? You might think that, oh, it's complicated, but however, you're going to have to take the derivative just in the respect of x, but leave the yz unless there's a constant, either you add or subtract. But since it's multiplication or division, this is multiplication actually in this case. So what you would do, since it's take the derivative, partial derivative in respect to x, I would say yz over xyz, then you cross cancel it and you get 1 over x. Or in other words, x to the negative first power.
Okay. All right. Yes, that is correct. All right.
Anyone with me? Anyone with me on track?
I don't think there's anyone with you. I don't think they're on whatever you're on right now. So
how many of you got the answer that I got?
Jason. Okay. All right, Abdul Rahman, you out there?
I thought I was doing f of z, so I was working on that. But let's give it a try.
Okay.
Can you scroll back up to the question?
So it's xe to the z plus ln of xyz.
So x e to the z would be a constant, so we would ignore that.
Mhm.
And then for ln of xyz, it would just be 1 over y. So
Right. And again, by the chain rule. There are a couple ways you can actually think about this, by the way. But it would ultimately become 1 over y because you'd have this. By the way, we kind of already know that in single variable terms, if you have ln of a constant times the variable, then the derivative is still just 1 over the variable. So for example, if you have ln of kx, the derivative always is just going to be 1 over x. Various ways you can see that. One, you can do it by the chain rule. It's going to be k over kx. Or two, you can use the log rule and realize that this is log of k plus ln of x. And again, you can just, this derivative is going to go to 0 because it's a constant, and then the derivative of that is going to be 1 over x. So tons of ways you can see that. So you could even think of the other two variables as just a k, and then you just get that. So pretty much that's going to what's going to happen here. How about f of z?
Oh man. Okay, so this one's kind of hard, but I'm pretty sure if we're looking at it with respect to z, it just stays as x times e to the z, and plus the chain rule of the second one, which is xy over xyz. But I think you could change it to 1 over z. Yeah.
All right. Okay. Good. All right. So if I'm to take account by the three of you, I guess we're all up to speed. We all know what we're doing. Okay. Good. All right. Let's go to higher derivatives. Oh, so now we're going to talk about things like second derivatives, third derivatives, etc. Right? And we can, just like how in single variable calculus, we can take first, second, third derivatives, and these guys all have their own interpretations. We're not going to worry about the interpretations right now. I just want to know, you guys to know how to computationally find the higher order partial derivatives. You will look at applications of them in the next class. So basically, nothing else to explain there. Once again, taking a higher order derivative just means you took a derivative once, and then you take it again. So now, what I do want to make sure that you are correctly identifying is the notation when doing this. So here's an example. Suppose I have a function f and I took the partial derivative with respect to x. And then I took the partial derivative of that with respect to x again. Then according to the Leibniz notation, very similar to single variable calculus, it would be d squared f over dx squared. That's how you denote it. Now, what would it look like in the subscript notation? Well, you would take the partial with respect to x, then you would take the partial with respect to x again. This we would call fxx. Now, it's very important, one thing I do want you to realize, that you do not write something like fx squared. We literally list out one variable after the other when we're actually taking the derivative. So you would write fxx. That's how that notation would work. Now, suppose I wanted to take, again, let's say I did the partial of f with respect to x. Then I took the partial of that with respect to y. This would be, of course, d squared f. And now it would be dy dx. That's how I would write that guy. Now, what do you think the equivalent would be? So let's say that this is the equivalent notation. What would be the equivalent notation for this?
Well, this
fxy, right.
Y.
So what you would notice here is that this would be fxy. Now, here's what I do want you to pay attention to. Notice that the order actually changed. So that's going to be very important. Here, this guy here over here, it's read pretty much in terms of the order in which it's done. It's left, right to left. Meaning the guy on the right happened first. Notice that the dx is on the right side in the denominator while the dy is on the left side, meaning dx occurred first and then dy second. So when you read this d squared f dy dx, the reader is supposed to understand that this person took the derivative with respect to x first, then with respect to y. This, however, is read the opposite way. This is read left to right. And so again, dx occurred first, then the dy. But the notations look in the opposite order, and the reason is because of where the notations are applied. When you use the Leibniz notation, you apply new derivatives on the left. The Leibniz notation is applied to the left of a function, whereas the subscripts notation is applied, new derivatives are applied to the bottom right. So because we're applying new derivatives on the left in one notation and on the right in another notation, the notations would look like they're in opposite orders. However, they're doing the same thing. I just want you to be aware of how to read them. Now, there are going to be times when the order does not matter, and we'll cover that. But in general, you do want to take note of the order in which things are written and understand what comes first, depending on which notation is being used. So that's very important.
Professor, I have a question.
Yes.
So if you were to take, for example, if there's a third variable, you would put dz outside of the dy. Would it work like that? And then you would put f.
Yeah, like you would have a d cubed f over dz dy dx.
Dz, and then the dz would be on the left side of
and the dz would be on the left here, and then that would be interpreted as you taking it first.
Oh, okay.
So if you saw something like, let me throw another example out here. So if you saw something like d squared d to the fourth f over something like dy dz squared dx. This means you differentiated with respect to who occurred first?
X.
X, then with respect to
C 2 times.
Z, and you did it twice.
Z.
And then
Y.
and then with respect to Y. So you, by reading that notation, should know whoever took the derivative, this is how they envisioned it. They did the derivative with respect to X first, then they took the derivative with respect to Z twice, and then they took the derivative with respect to Y. And in the equivalent notation, you would write down something like completely going in the opposite order. The Y would end up all the way to the right side, and the X would end up all the way to the left side. But they're literally the same derivative taken in the same order. So that's just what I wanted to be aware of. So there's a little quirkiness with the notation, but this is because the different notations are applied on different sides of the function. And so they're kind of read in opposite orders, but you should know in the subscript notation, the guys that are on the left occur first, whereas in the Leibniz notation, the guys that are on the right occur first. Okay. And I already kind of did an example here, but maybe fill these guys in. So Jason, give me the subscript notation for this one.
Oh, I could tell you this. All right. I would say f to the base y, x, x, x.
That's 6 derivatives.
Well, look.
We're doing this one here.
Oh, you're talking about, I thought you were talking about choice part B. Oh,
no.
This one of part A? Oh, so part A would
See,
be
you're
F,
you're
Y,
jumping
X,
ahead of
X.
yourself. Come on. Okay, so what is it? F sub
Y, X, X. the
Okay.
base.
And I was gonna call out Natalie, but you totally just stole her thunder, so I'll just finish here. All right, great. So we understand how the notation happens. All right, let's move on. Okay, so here's what I want you to do, another example. I want you to find all second order partial derivatives of this function. So now, here is a two variable function. So when we say all second order partial derivatives, this basically is saying, I want you to find fxx, fyy, fxy, and fyx. All right, so with a two variable function, you'll have four possibilities. With three variables, it starts to go up by a lot. It starts to go up by like 6 possibilities for the next one. Or so, okay. Oh, it's actually even more than 6. Anyway, let's go. The middle terms. XXX, is that what you're laughing at? All right, so if I want to find fxx, what do I find? I want the first one. What do I need to do? This a little bigger, make sure you guys can see. Too big, maybe. Okay, that's fine. Right, get fx first. What's fx?
Fx, well, I would say 6x subtract 6x squared y plus 3y cubed, and you would get minus 0, simple as it is.
Okay, and so what is fxx?
Fxx, oh, easy. 6 subtract 12x y, and you would get 0, simple as it is, like at the end, plus 0. That's what I mean.
All right. Okay, so now fyy. So we'd first find the partial with respect to y. Well, let me, because I'm gonna forget what this guy is. People already. Yes, I'm with you, Jason. I'm following.
No,
I'm
just talking to the students. Just talking to the students. Are you with me and Jhevon?
Oh, okay. I thought you said with, okay. Like you're carrying their energy. You're the mascot right now. Okay, so with the fyy, the derivative of 3x squared would be 0. Then we'd have the derivative of that would be 2x cubed. Then we'd have this derivative 9xy squared. Then we'd have 8y cubed. Then you'd find fyy. Derivative of the first term would be 0. Then this would be 18xy. Then this would be 24. Oh, someone is typing in the. Oh, you typed the one that I already put down. You're typing too slow. 24y squared. That would be fyy. Now, if I want to find fxy, basically what I'm going to do is I'm going to go x to fx. I'm going to differentiate with respect to y. So what was that guy? I think we're done here. So that was 6x. I'm going to differentiate that with respect to y. So this is minus 6x squared plus 9y squared. And that's my fxy. And then for my fyx, that would be partial with respect to y. Then I take the partial with respect to x. So I start here at the partial with respect to y. I'm going to start here. and differentiate with respect to x. So that's giving me minus 6x squared plus 9y squared. And that's that. And Natalie noticed, hey, these guys are the same. Coincidence? Well, almost. It's not a coincidence that these two were the same. We actually know that. There's actually a very important theorem. It's called Claros theorem. It's one of those French guys. I always spell his name wrong whenever I'm writing it on a board, but that's guy. So one thing you can notice is that when I took the partial derivatives in another order, it turns out that they're actually the same. Now, is that going to happen in general? The answer is no, right? So what you want to do, well, I don't know. Well, I'm not really going to talk about like where it comes from or anything like that. I'm just stating it as a fact. So I'm kind of cutting out all the beautiful parts. If your function and all its partial derivatives are continuous at a point, then it means that the order in which you take the partial derivatives don't actually matter, right? So this is called the mixed derivative theorem or Claros theorem. And it's basically saying if you're continuous at the point, if all of your partials, the original function and all the partial derivatives are continuous at the point that you're taking a derivative, then the order in which you can do it won't actually matter, which means it also extends beyond two variables. Of course, to justify that, you need something like a proof by induction, but this works with more than two variables also. Just as a pro tip. So for example, if everyone is continuous, then if someone went and say, okay, I'm going to take the partial with respect to x, then with respect to y, then with respect to x twice, then with respect to z, then with respect to y again, and someone else says, you know what, I'm going to take derivative with respect to x 3 times, then I'm going to take derivative with respect to y twice, then a derivative with respect to z twice. And then, let's move this. Versus. And Jason's like, no, here's what I would do. I would look at this and then I would say, and then he'd basically come like, everybody with me. I want to go Z first, then the 2 Ys, then the 3 X's. And it turns out that these guys here will all be the same. It doesn't matter how many variables there are, how many times you're doing it, all the same. However, it's very important that you do need continuity. So let me actually write out continuous. It's very important that you cannot assume this is true unless everybody's continuous. The moment one of these guys might have like a division by 0 or like a negative under a radical or something like that, the moment anything like that happens, then the order definitely matters. And you can end up in trouble because you're going to think of derivatives as being the same, but they're not. So Claro's theorem says, as long as the function and the partial derivatives are continuous, then the order in which you take the partial derivatives are going to give you the same answer. Now, this is nice because one, it will allow you to get away with a lot of stuff. So for example, suppose I had this example right here, and I wanted to find the second order partial. Right, so here's an example. Z equals this, blah, blah, blah. And I want to find the partial, the second order partial of Z with respect to X, then with respect to Y. Or that's not scary. It's actually not scary. Suppose someone said you wanted to do that, right? So now when you read this directly, then what this means is you'd have to take the partial of Z with respect to Y, And then you take the partial of z with respect to x. And this happens after. But, big but, I like big buts. Anyway, notice that taking the derivative with respect to y, we would end up having to actually take the derivative of this whole thing. Does anyone even remember that? Let me just give you like an impromptu test here. What is the derivative with respect to y of 2 to the y? Do we remember what that is? Jason, you remember what that is?
What?
The derivative with respect to y of 2 to the y. This down here.
Respect of a y to 2 to the y.
Yeah.
Well, I mean, like, if it's to 2 to the y power, I mean, like, the derivative of it would be just like, 2y, 2 to the y power times ln z, times, actually, hold on. 2 to the y power times the derivative of y, which is 1, times ln of 2.
Right. So it's 2 to the y ln 2. Okay. So we do know if we're forced to do it, we can do it. Okay. However, notice that to take the derivative with respect to y, that would we need the quotient rule. For like this term over here, and then it's like yuck, right? So it's like however, notice I probably should have put the but down here. Could put 2 buts. Like big butts, why not? Okay, but notice we're continuous. Since as long as y is not 0, and it's not, everybody's continuous. Why? Because the arctangent to get the arctangent of 0, your y would have to be 0, and then you would divide by 0. But as long as your y is not 0, you would not divide by 0. And how do I know it's not 0? Well, I'm dividing by arctan of y. So it's not, since we're dividing by arctan of y. It would be nonsensical if the y was 0. Well, y cubed, but it's the same thing. So we have continuity. And so Claros' theorem would tell us that the partial of z with respect to x, then with respect to y, is actually equal to the partial of z with respect to dy dx. Now, when you look at it that way and you go up top, notice what happens. The partial with respect to x is easy for this guy. I don't need quotient rule anymore, because as far as x is concerned, that guy's a constant. So that just goes to 0. Then I would have to take the partial with respect to x of this. So that just leaves me with y squared. And so that's just 2y.
Why?
You notice that that's literally a lot easier than if someone were to just take this at face value and run in and try to just, let me take all derivatives, quotient rule, right? Now it's like, but it's continuous. So I don't have to follow your order. I don't have to follow your rules. I can follow my own rules. I can go in whatever order I find convenient. So Claros' theorem is very convenient and handy for that. However, you have to be aware, in order to do it, you need to make sure that the region in which you're doing it, you have continuity, because it is not true in general. Okay, so that can help us solve some issues here. All right. Another example, just for some fun. How do you know the region? Well, in this case here, This would be continuous everywhere because the only possible issue, because this part is a polynomial and the top is an exponential, the only possible issue would be a division by 0. And I know that a division by 0 would not occur because they wouldn't even write this down in the first place. Other than that, it really depends on context. So maybe you're doing a problem where they ask you to find the tangent plane at a certain point. So you'll have some reason to know the location. So it's not all the time that you just want to take the partial derivative in like some sort of generality. A lot of times, we did some examples up here. A lot of times you're going to find the derivative at a certain point, right? So you're going to kind of know based on context what the location is. I mean, there are times where you're going to have to think more generally and you would have to say to yourself, well, what I'm doing here would only work as long as this variable is not this value. You would say that. But a lot of the times you do know from context what your location is going to be. And then you just make sure that at that location, everyone's continuous. And then then you're allowed to use Claros theorem. Another example. So three variable function. And I want you to find a couple third order partial derivatives. Okay, Jason's just really excited. Jason really loves partial derivatives. I didn't know. Okay, Jason, go. Give me the first one.
Okay. F base z z x. Well, take a look here. What do you have here? Well, if you were to think like, about the partial derivatives, you see, like in the x, right? The partial derivative in respect to x would just be like, I would just say like y e to the x power, like, and after that, then you would get like, ln z, just plus ln z.
Okay.
Then if after that, once you did that, then if you were to think about the second, partial derivative, which is in respect to x, it would just be 1 over z, and ignore the y e to the
You
x
mean
power.
z? Okay. And then?
And after that, then you once you did that, then you take the derivative of 1 over z, like, which is z to the negative first power. You would get negative 1 z to the negative square, which is like, negative 1 over z square.
Right. And this is in fact equal to this, that. Why? So you literally just took the derivatives in a different order than was presented. How do you know that was valid, man?
Because Claro's theorem, just easy, just simple, just apply Claro's
don't tell me
theorem.
Claro's theorem. How do you know it's continuous? How do you know z is not 0?
Because look, if you were to plug in 0 for z or z, it would just be undefined.
Right, the original function doesn't work. So you had to make a note of that. Notice here, the fact that this is already there, which means automatically you know your z is greater than 0. So you're allowed to divide by it, right? So continuous.
Professor, I have a question.
Yes.
So automatically, if they provide us with an equation, then we know for a fact that it works, or we're not supposed to test it out or something?
I mean, if I were to tell you, okay, look at the equation y equals 1 over x, would you ever even imagine that x could be 0 if someone just stated this?
No.
No, right? So you would realize that mathematically speaking, at certain values, some things are just so nonsensical that yes, technically, if they're going to be pedantic about it, they should put x not equals 0. But this would kind of be assumed by the reader, right? So it wouldn't make sense for us to actually write. It wouldn't make sense for us to write down ln of z if the z were 0 or anything negative. Now, yes, if you're in a complex analysis class, you could assume that the z could potentially be negative, but then you deal with that in the context of complex analysis. But yeah, you are assuming that when someone writes down a function, it would have to be given, you would have to know that you'd have to avoid something. If they wanted to tell you something else going on at 0, they could do a partial, a piecewise function. They could say it's like a xe to the z plus ln of z if your z is not 0, if your z is greater than 0, and then they'd have to tell you something else. So, and it's equal to y if your z is less than or equal to 0. So they'd have to mention something. Otherwise, you would just kind of know that I'm not allowed to plug in that z because there's an ln here. So if there's something else that you should worry about, that's not like blindingly obvious, it can't be that thing, they would actually tell you, okay, we know that at z equals 0, there's a problem, but here's a redefinition. So within context, you'll kind of know how to handle yourself. At this point, you've gone through algebra, pre-calc, calc 1, calc 2. You kind of know when certain functions make sense and when they don't. So unless they specifically tell you how to deal with a nonsensical situation, you kind of just assume that that situation isn't in play in the first place.
Yeah.
Yeah. All right. So let's, so that was that one. Now, what about fxxz?
Could I do it, Professor?
Sure.
So since we know that it's continuous, the order doesn't really matter. So we could just do a look at the derivative of y equals, so f of x equals
What do you mean f of x?
like the partial differentiation with subscript x.
Oh, you call it f sub x. You don't call it f of x. Yeah. When you say f of x, it means this. You want to say f sub x or partial with respect to x. You'd have to use those phrases.
Okay.
So we'd call this f of x. We'd refer to this as f sub x. And we'd refer to this as partial with respect to x. That's just kind of how the everyday language that we'd use.
Okay, gotcha.
All right.
My bad. So for the first part, we're gonna do with f sub x.
Yeah, we already have that.
Yeah, the first one I was about to say y e to the x plus ln of z.
Yeah.
And then when we do f sub xx, it would be the same thing, y equals x, but without the plus ln of z. And then
Right.
it would be just with z, I mean, since there's no z, I think it would just be, honestly, I'm lost. I think it would just be y to the x. Just zero.
It would be 0 because there are no y's there.
Yeah.
Why isn't it just y to the e to the x powered? Like, you know, I mean, like if there's no z's.
Exactly. So if I told you, think single variable, if I told you my f of x was 5, there's no x. What is the derivative?
0.
0. Right. If there's no x's, it's a constant. Same thing here. There were no z's. There were no z's. So as far as the z is concerned, that's a number. So that's 0.
Would it have been better to do f sub z from the beginning?
Right. Now I was going to mention that. So notice here, to get to this 0, you actually went through 3 steps. You did the f sub x, then the f sub xx, then the f sub xxz. Or you could have noticed that your you could have first done fz. That means you could immediately eliminate this guy. And then here you would have gotten what? X over Z.
X over Z, yeah.
And then you do the FZX. This gives you the 1 over Z. I mean, it still worked out. It still worked out, so you have to do it 3 times. Never mind. Okay. Well, one day, what I'll do is I'll put one example where there are like 5 derivatives. If you take it in one order and it's actually only 2 derivatives in the other order, maybe I'll put something like that on the test. Who knows? And let's see if anyone just jumps in and just immediately goes for the order in which it's written. You should be aware that yes, you're allowed to take different orders as long as it's continuous. I would assume for something like this that it is continuous wherever we're taking derivatives, because the only problem would have been if Z is less than or equal to 0, but you kind of wouldn't write this down in the first place if that were the case.
Could you give us an example of where we could recognize that it's not continuous?
Maybe there's going to be an example later on. That can work. Okay, now let's talk about differentiability. And I'm going to give you a word example right here. I don't think that's a... I don't think that example would work for as a Claros theorem example though. Let's see. Can I think of an example where Claros theorem would fail? Yeah, I think the examples would look really nasty. It would look like some sort of piecewise function. Yeah, so some that you can like write down in the way that we normally write things down. It would be hard to come up with an example, but I had looked one up earlier. Example where Claros theorem fails. It's really not an example that you would know off the top of your head. It's going to be very exotically written. So something like that is an example. The second order partials close to 0 will not be the same if you look at that. So you guys can actually try to work that out. You will actually find that like your second order, if you take with respect to X first and then Y, let me write this down. Do the quotient rule. Yeah, you get like -1. And if you take respect to Y first, then X, you would get +1.
Professor,
So
what I think I'm sorry, speaking of this problem where it says the example where Chloride's theorem fails. Speaking of Chloride's theorem, what you can figure out is that speaking of Chloride's theorem, it's only continuous. Like, you know, as long as it's like, you know, continuous, that's all that matters. But however, according to this problem, I mean, like, what I could tell you here.
Oh, you don't think it's continuous?
You know,
all right, Jason has doubts it's continuous. Can anyone verify that this is continuous or
well,
not?
I think it's actually continuous because want to know why actually? Because
Why
if
is
you
it
were to think
continuous?
about continuity, like, you know, you can, if you were to determine the limit of xy parentheses x squared minus y squared over x squared plus y squared, you know, the limit would just be 0. And, you know, even though it says x, y does not equal to 0, 0, and however, parentheses for 0, parentheses xy equals 0, 0. According to what I determined here, I think it's continuous.
So what would, how would you, so I didn't hear what you said. How would we check if this is continuous at the origin? What is the general process? Tell me in a sentence.
Think about continuity, like, you know, this is a piecewise function, right?
Yes. What does it mean?
So what I determined, so you see this, like, you know, the first part, xy produces x squared minus y squared, you know, over x squared plus y squared. What you can tell is that if you were to plug in, like, you know, y to 0 or x to 0, or like, you know, y to kx squared or y to kx or anything, the limit would be 0. It wouldn't be,
Okay, so you have to check the limit. So you need to check that the limit, that's what I want you to say. Limit of xy at 0, 0 of f of xy equals f of 0, 0. And you can do this. One way to do this nicely, quote unquote, nicely in your head would be, you could, for this particular problem, I would do like the polar coordinates strategy, right? Doing it that way, you'll notice that from the numerator, you'll be able to factor out an r to the 4th. From the denominator, you'll be able to factor out an r squared. Then you'd get an r squared in the top and just times a constant, then divided by a constant. R is going to 0. So this limit is actually 0. So
yeah, that's what I just said.
So f is continuous at 0.
Yeah, continuous at 0.
Now,
so
where the problem happens is when you do the partial derivatives. I think the partial derivatives themselves weren't continuous at 0. So if you were to do the partial derivatives and then do this check, there comes a point where it breaks. You guys can try it. Show why. Claros theorem. I don't want to say fails. It doesn't really fail. Fails as in does not apply. If you tried to apply it, you would fail. So the original function is continuous. So yes, you saw that and it's good. You should be able to see that. The continuity breaks down once you start taking derivatives. There is going to be another, and the example, I thought the example that I gave later could have sufficed for here, but it would not, because the example that I'm giving here is actually quite the opposite. And this is what I want to talk about in this section, is how the partial derivatives world can be very strange. Because it turns out that this function here is not continuous at 0, 0, yet you can find partial derivatives there. So let's actually talk about differentiability. All right. So there are a lot of things that we know about differentiability from Calc 1. And like I said, like we've been saying here, the partial derivatives, hold on. It must be due to conditions and just, oh, well, I'm not, Yusuf, I'm not sure what you were referring to at this point. And I hate to break it to you, but your last sentence is actually not true, but don't worry about it. By the time you get to the level, so yeah, Yusuf was, I enjoy the positive emotion around everything, thinking that everything is gonna have a solution, everything's gonna work out. Yeah, you know what? No matter how tough it gets, there's always a solution. Unfortunately, no. there are a lot of problems that don't have solutions. And there are, and to be even stranger, there are a lot of problems that we cannot even prove whether or not it has a solution. So we have literally no idea, and it's literally impossible to ever know. There comes a point in math where you grapple with certain uncertainty principles, where you come up with problems that it is impossible to know not only what their solution is, but to even know if a solution exists. The world gets bigger, and it's a lot interesting. You can look at the theorems would be called Girdles incompleteness theorems. It seems frightening, but it's actually very interesting. And so, yeah, it's literally the case where people think that they can get the math to work out whatever they did. Kind of like how when you had complex numbers, you're like, oh, x squared plus 1 equals 0, can't solve that? False. I'm going to invent a solution. Let me say x equals I solves it. And then you're like, okay, and you invent complex numbers and you're like, all right, everything's hunky-dory. There comes a point in math where even if someone were to make up an answer as a solution to an unsolvable problem, it won't work. It will literally break math. So they're just not allowed to do it. Don't worry, if you're not a math major, you will never have to deal with that. So yes, if you're not a math major, then in your universe, everything has a solution. Everything will work out. If you're an engineer or you're a physicist, yeah, things will work out. It'll be fine. The math people will deal with the really, grapple with the really tough things. Okay, so just had to stop there. I'm sorry, I went off on a tangent, but his comment I had to, all right. So let's talk about differentiability. Some weird things can happen with differentiability. What I do want you to remember is, yes, we're doing partial derivatives and rant number 430. Yeah, we're doing partial derivatives, but I don't want you to get the impression that a partial derivative is a derivative. Again, it's only the derivative from a certain perspective. The total beast, the total derivative, is something completely different. And there are times when a partial derivative might work or not work. And there are things that you would think that it would be able to tell you about the scenario you're dealing with, but it just doesn't because it's not comprehensive enough. So it is still true, facts like if something is differentiable at a point, the function is continuous at that point. Yeah, that's still true. But there are other things that are very weird. For example, in this example right here that I listed, the function itself is discontinuous at that point, but computationally speaking, you can actually find the partial derivatives at that point. This is a function that we looked at last class, maybe the class before. We actually proved that this is not continuous, right? Approach along x equals 0, you get 0. Approach along x equals y, you get a half. So it's not continuous. However, it turns out you can actually prove that f not continuous at 0, 0. But, love big buts, the partial with respect to x at 0, 0 does exist. You can actually compute it to be 0. And the partial with respect to y does exist, and you can compute it to be 0. And so you'll have weird things like that. So, oh my God. Does your dad make jokes like that all the time? I don't know. Anyway, so differentiability is a weird thing in higher dimensions, and it's going to be very, oh wow, now things are getting too real. Okay. Now, it's going to be very weird. So some things I want to tell you about this is that differentiability in terms of partial derivatives, it's very hard to determine them, but you can determine them through these two theorems here. Now, these guys are mentioned in the in your textbook. I have to say, I don't really see them ever actually coming up in a final or anything like that. I really put them here for completeness. Basically, you can say a two-variable function is differentiable at a point if this equation holds. And you can say something like, if all partials are continuous throughout an open region containing a point, then it's differentiable at that point. The issue with these guys were they weren't continuous at an open region containing 0, 0. They were literally only continuous at 0 and along a line passing through 0, not in an open region. So that's why this weird example shows up here. So derivatives get really weird, and that's because, partial derivatives, I should say, get really weird, and that's because partial derivatives aren't the full story. And again, a lot of you will never really know the full story. When you're a math major, eventually when you take Advanced Calculus 2, you're going to learn fully what the full derivative is. And you're going to realize that what you've been thinking of as the derivative is kind of like a shadow of what the derivative really is. But the derivative is like this huge matrix, and when you get that matrix to work out, what all the consequences are, what it all implies, and what it means. In the meantime, I would probably only know this one, take time to know this fact right here. It's still true that if you can differentiate, if you know that the derivative exists, then the function is actually continuous at B. If the function is differentiable, yes.
Will differentiability be on Saturday's exam?
No. So in terms of what you need to know for the exam, above this is fine.
What about the final?
Down here, this is kind of a just in case. What I would say for below here is just kind of know what these things are in the box. You'll never have to actually justify anything. And again, I don't anticipate them coming up, but because, again, for these 2 semesters, because we're doing everything multiple choice, I'm always just kind of suspicious that they're going to put a multiple choice problem where they ask you about some obscure statement in some obscure theorem, and that they're going to put that as a question. I'm really worried about things like that happening. So sometimes I'll just put something in as a just in case. By the way, just know this fact that I put in a box. Just in case it comes up. You'll never have to actually calculate anything with it. But just in case someone ever says something like, oh, is it possible, state which of these statements are true, and they were to say something like, well, f is not continuous at the point. Does it mean that the partial derivative doesn't exist at the point? And it turns out that you would say, no, that's not true. You know, so I just wanted to be prepared for little mind-boggling questions like that. However, as far as we're concerned, everything that I taught you before this, the computational things about partial derivatives, that's definitely what you need to know. That's definitely going to come up. Differentiability, I just want to point out to you that in higher dimensions, things get, weird is the wrong word, but when your concept of differentiability is based on Calc 1 and Calc 2, then yes, it's going to seem very weird. So I just want you to be aware of that. And yeah, with that said, we're done. On that confusing note, we're going to end. We've finished the syllabus. That's it, guys.
Will differentiability be on our final?
No, I feel like I answered that.
And I said test 2, but not. I'm talking about the final. Unlike I didn't say anything about the final.
Oh, so I don't know exactly what's going to be on your final. It wasn't on the spring final at all. And I am 99% sure that it won't be on the final. But there's always that 1% of uncertainty when I have no control over the final. I'm literally going to see the final when you guys see it. Like the day of is when I see the final. So I don't really know for sure what we can say. As far as the final is concerned, I guess since we're pretty much done, I can just rant a little bit about what I do kind of know. Yes, so someone told me today that the second mock test that I have on the class website isn't working. I will fix that. I'll fix that right after class. Now, for the final, again, I don't fully know. I think they're going to change the format slightly, but I can tell you what it was like in the spring. It was 25 problems, and you had 2 hours and 15 minutes to do it, which automatically means if you're in my class, you're ahead of the curve right there. And my class was also ahead of the curve for that final in the spring as well. So I had several students getting 100s on the final, which I'm hoping to have a repeat performance in this class. So yeah, if you can get through my test, in all likelihood, you are over prepared for the final. You will be able to do the final in half the time or less. Most of my students actually did the final in half the time. They were done after an hour and a half. And it was crazy. So it was crazy how early they finished. And I had a bunch of people getting like 100s. So I don't think the final, in regards to everything, if you went through my written practice test and you went through my multiple choice practice test and you now understand everything, you studied the way I asked you to study, then in all likelihood, you're literally over prepared for the final. You should be able to like wake up on the wrong side of the bed and, you know, be half distracted and still pass it. Anyway, don't take any chances though. Be sure for the final to get a good night's sleep. Practice hard up to like 2 days before the final, the day before and the day of. Practice a little bit, you know, just to make sure you're not forgetting everything. Go over your rules, go over your definitions, go over your strategies, practice some problems here and there. But in the meantime, between now and then, what you do want to do is you want to practice full finals, do practice tests, and that's how you're going to prepare. Basically, follow the strategy that I posted on the class website. How I told you to study for tests, you're going to do the same thing with the final, just you're going to be doing it with a cumulative set. So everything that was on my test 1 and on test 2, you're going to make one test out of that. It's going to be too long if you take my test, but practice the past finals on the 212 website and the practice finals on my website, and you should be nice. Yes, the final is multiple choice. It will be on Blackboard. One other thing that's going to be, that's another thing. Let me write that down. Make sure you can log into Blackboard. And see our class. Very important. You don't want the day of the final, you don't know how to log into Blackboard, you don't know your password, and then you get in and then you don't see Math 212. You need to make sure you can log into Blackboard. That's very important. Another thing that's going to be different to the final from our test, in the spring, you are not allowed to see the entire test at once. So that's going to be different. So when you're looking at a problem, you cannot move forwards, you cannot move backwards. So you're going to start the final. Problem 1 is going to come up. You have to complete problem 1 before you move on to problem 2. Once you move on to problem 2, you're not allowed to go back to problem 1. And once you're on problem 2, you're not allowed to go forward to problem 3. The moment you go forward to problem 3, you can't come back to problem 2. So the final is multiple choice, but it will be linear and you can't move forward and backwards. So whenever you get an answer, you have to make sure it's the right answer, double check your work, and then move on. Which is kind of why I was really tough on my class and I wanted them to be able to do a lot of work in a short amount of time. So if you look at one of my tests, if you look at itemized things that you needed to do, you did about 20 things in an hour and a half, which means if I give you 25 things to do in 2 hours and 15 minutes, you will have extra time to double check your work on every single problem. So that's what I was training you guys for. I essentially want you guys to be able to do a final almost twice as fast as someone would expect you to be able to do it, because I would expect you to have to double check your work, make sure you're not making any silly mistakes, make sure you're getting everything under control before moving on. So in the spring, you weren't allowed to see the entire final all at once, and you weren't allowed to navigate through the questions ahead of time or navigate back to them. So really, that's the only aspect of the final that will be more difficult than what I have. But again, by that same token, if you can survive my tests, you're gonna survive the final. I don't see. Yeah, quizzes, I'm giving you like 14 problems in 20 minutes. Like it's not, yeah, it's serious. It's ridiculous, isn't it? Yeah, so in the spring, the final was around 25 problems. I assume it's going to be very similar. I don't know for sure, but I don't think they would change it too drastically between the spring and now. But in the meantime, make sure you can log into Blackboard. I will make sure to make the mock test 2 live. And then, yeah. And Kayla, stop your nonsense about B+. A, everyone's supposed to head for an A. Yes, A, everybody. A is what you're going for. A+ if you're a show-off. It's fine. If you want to show off, A+. All right, we'll just, all right, he's a show-off, okay. But A, all right? I don't officially curve, but I do take improvement into account. So if you were shaky on some of the quizzes, you were shaky on test 1, but your test 2 looks good, your last quiz looks good, your final is awesome, then I'll kind of turn a blind eye to the failures of the past, let's say.
Like, what do you mean? Like, what are you talking about? Let's say if I have, like, if someone has a 77, like, you know.
I'm not gonna get into specific numbers. That's not, because then there are 1,000 different scenarios that I could get into. Like when I give you guys grades, I really take everything into account. I literally spend a really long time on every single name and really try to think of ways to give them the best grade possible. So I'm going to look at how many homework assignments did this person complete? How did they do on their quizzes? How did they do on their tests? How did they do on the final? Did they participate? Did they, you know, I'm going to try to look at the total person as an individual. Okay, so it's really not something where I can just say, oh, what if someone got a 77 and then they got a 89? Like, I don't know. I still don't know. It would depend. Okay, hopefully, the hope is that the final won't shake you. Okay. Well, thank you for that. You guys were a great class too. I'm not just saying that. I had a lot of fun. But yeah, I guess, yeah, we're kind of done there. Like, I mean, we wasted a lot of time clowning around today, and we still finished ahead of time. Technically, if I wanted to rush, we could have finished yesterday, but I didn't really see a reason for there to rush. I mean, we can relax. Unless, oh yeah, Nettie's a good friend of mine. By the way, back when I used to, so if you watch some of my old videos, you'll notice Nettie's voice in the background. She used to be my camera person for a while until I started just leaving it as a still picture. Yeah.
Speech.
Nettie,
Speech.
What? No speech. No, not today. Today is not even technically the last class. I'm seeing you guys on Monday.
So are we reviewing on Monday, or what is it going to be?
Yeah, so Monday it's going to be a review. So basically, hopefully over the weekend, I'll find out more about your final. I'm hoping to find out more about your final. So whatever I find out on Monday, if I have any new information to give you about the final, about the format and anything, I'll do it then, as well as, yeah, maybe you went through the second test and you have some concerns, right? Then I would deal with those on Monday as well, just to kind of get you in the right mindset for the final and how you want to go about doing it. So the final's on Thursday. So I really want to make sure that by Monday, you're definitely on the right trajectory. And Monday is about getting you guys on that trajectory so that Thursday is going to go very well.
Also, Professor,
Yes, come with questions for sure. If you're showing up, come with questions.
The topics for test 2, is there a way we could look at which topics were on it, just in case we want to like dissect each topic one by one?
Yeah, I guess you can look in the syllabus if you want to go that route. But the test 2 is literally everything we've done since test 1. But in the syllabus, you should see it. Now, my page always takes a long time to load because I have all this documentation in there.
It's on the math website, right?
Yeah. Go to the math website, go to people, click on Jhevon, then click on our class, then click on the syllabus. The same page where you find all the practice exams where I have to fix the mock test too.
Professor,
Right,
I'm trying to see you, like, you know, after class, like,
yes,
you know.
I remember, Jason. I'll send you the link. Yeah, so test 1 was everything up to series, remember? So test 2 is everything after series. So it's going to be parametric curves, applications of series to integration, polar coordinates, 3D space, vectors, dot product, cross product, lines, planes, cylinders, quadratic surface, functions of several variables, limits, and partial derivatives. So if you look at the syllabus, it tells you right there. So our test 2 will cover everything from section 10.10 onwards. So it starts at using series to evaluate integrals. Then it goes into parametric equations, polar coordinates, all the 3D stuff. Yeah, so I just told you the section where it starts. It starts at 10.10 and goes down. It's in the syllabus. 10.10 to infinity. So what's 213, beyond infinity? Yeah, so the test Saturday 12 to 3 is going to be the window. Test 2, Saturday, grade scope, 12 to 3. The test, again, hour and a half to do 20-ish problems. Some conceptual, some calculation based. So from whatever time you start, it'll only give you 90 minutes. But at the end, at 3 o'clock, you need to submit everything and including submitting scans. So be sure that you start early enough. If you know that scanning gave you an issue last time, start earlier rather than later.
The scanning, like we said before, it's not part of the hour and a half because it's like a different section, correct?
Yes, it's a different part.
But it has to be done before 3.
That has to be in by 3, yes.
Okay, gotcha.
Jason, you always ask me the same thing, concepts. Just like take a cue from all the quizzes that I've been giving you. I'm not sure what you're talking about, Fahim, but email me and let me know. Anyway, I think we're going to end because right now, I mean, it's cool for you guys, but anyone else watching this video, now they're just sitting here watching, wondering if I'm going to say something important. And I'm just like, we're just like talking, not really saying anything important to Calc 2. All right. So let me just end here. Jason, I will send you a link for office hours and I will see you guys on Monday. So that's it. Take care, stay safe, and I'll see you in the next one. Ciao.